So we have, after this, another theorem. So let's again let psi AB be a bipartite quantum state. And I want it to be pure again. Then the theorem is that rho A we know is the trace over B of rho AB. Rho AB, of course, being the outer product. And the other reduced density matrix, rho B, trace over A, rho AB, have the same eigenvalues. Okay. So this is something that the Schmidt decomposition enables us to prove. And without this, it would be somewhat unclear or perhaps even surprising that this is true. So let's see how this goes. Proof of this one. For rho AB being this outer product, psi AB, I know that I have a Schmidt decomposition for each of these psi's. And so I can write that sum over I, lambda I, IA, IB for ket psi. And then I'll do the same thing for bra psi. You just need to be careful that you use a different index here. It wouldn't be the same index, I. It's a different independent index that you're summing over. But other than that, it's going to be the same thing. So psi j, lambda j, j a, j b. And so from this, you can simplify as sum over ij, lambda I times lambda j, and then we'll have II a tensor j b. And we're using, to go from this step to this step, the linearity property, of course. So now this gets us ready to evaluate the partial trace. Okay? So I'm going to have to do the partial trace over B and the partial trace over A. And what's going to be a convenient basis to do that? Well, it's going to be the ones that we see here. Usually it's obvious which basis you want to use to evaluate the partial trace. And so for here, it's going to be the basis I for subsystem A and or the basis J for subsystem B. So let's do one of them. So rho A being the trace over subsystem B of rho AB, that will be equal to sum over K to trace out the B subsystem. I'll do identity on the A subsystem and basis vector K on the B subsystem. Rho AB, identity tensor K on B. Okay, so just the definition of the partial trace here. And I have a different index K because it's independent, but I'm thinking about using the same basis J that we have for the subsystem B. So when you do that, it's going to kill the summation. You're going to get a delta JK for each one of these. And so what you'll end up seeing, and that's just by orthogonality again, what you end up getting is that this is equal to sum over I. You'll get a lambda I squared, and then you'll get the I basis for subsystem A. Okay, so I'm just sort of telling you the results, but make sure you could reason through that and evaluate the partial trace of this guy. Again, all you're using is orthogonality. What you'll end up seeing is that you get lambda I squared for the eigenvalues. And when you do the same thing for subsystem B, you'll see something similar. Rho B is equal to the trace over A, rho AB. and that will end up being a sum over I lambda I squared basis vector I for subsystem B. Okay? And from this, you can very easily see that the eigenvalues of row A are indeed the same as the eigenvalues of row B. They're the square of the Schmidt coefficients. And these lambda i's we call the Schmidt coefficients. And so that proves our statement for any bipartite, pure bipartite quantum states. The reduced density matrices actually have the same eigenvalues.